All right, let me do a quick sound check. That all sounds good. And do I see things moving? Yes, I do. And it doesn't look like I'm experiencing the same lighting issues as last week, so I think I have fixed that visual problem. Okay, let me put away the headphones. And let's get started. So, I'm not as prepared as I would have liked to be for this, but I do have a general idea of what I want to do today. So, it's been several weeks since we did what we did with Riemann sums. I remember not liking the way I explained some things. For example, this thing with the spherical shells, I felt like I didn't really justify it properly, but now that I've had several weeks to think about it, I think I have a new way to justify what I did here. I think that was probably the worst part of the last time that we did any math-related stuff. So that will probably be next week or the week after, depending on whether or not I think there's anything else we need to cover before then. But yeah, we'll see. We'll be following up on Riemann sums. We're still building towards that, especially for the physics students that have been stopping by my channel recently. I might prefer to have this sort of material ready to go for them in case they are further ahead. But yeah, today the goal is to just go over a couple of calculus techniques, which some people may have already learned, but it doesn't hurt to go over them for the students who don't know. Plus, there's going to be, even for the students who have learned some of these calculus techniques, I have a little bit of a twist prepared. And actually, I need to have that preset, yeah, so that I don't accidentally pick the wrong thing later. I think I'll be able to show those students that they might not be as good with their integration techniques as they might think. So, where do I want to start us off? So, in our discussion of Riemann sums, I introduced the power rule for integrals. So I introduced an integral that has this form, x to the n, integrated with respect to x. And I demonstrated, at least for x squared, that the power rule works if you do a Riemann sum. But the general rule, the general pattern you'll find, and if you really want a proof of this, I know Khan Academy has a proof for it. It's going to be x to the n plus 1 divided by n plus 1 plus a constant. So you increase the power by 1 and you divide by the new power. This is called the power rule. Now, the great thing about the power rule is that it works on a lot of functions. It's not just for polynomial functions. It's not just for things like x squared, x cubed, x to the fourth, and so on. It also works for fractional powers. It works for something like the integral of the square root of x. The square root of x can be rewritten as x to the 1/2. And if you can't easily jump from here to here, then you might want to review your laws of exponents. You might want to grab a pre-calculus book and just review that for a little bit. But yeah, you can rewrite it as x to the 1/2, and then you can just use the power rule on it. So you would go 1/2 plus 1, and then divide by whatever 1/2 plus 1 is. So you would do x to the 1/2 plus 1, that's 1/2 plus 2/2, which is 3/2, and then divide by 3/2, which is the same as multiplying by 2/3. So you get 2/3 x to the 3/2 plus a constant. So yeah, the power rule works on fractional exponents. It also works for negative exponents. It also works for negative exponents. So you could do something like, let me think here. You could also do something like 1 over x cubed, for example. You could rewrite this as x to the -3. And then you could go, well, -3 plus 1 is -2, so that's x to the -2, divided by -3 plus 1, so divided by -2 plus a constant. And then, of course, we would simplify and rewrite this as -1/2, pulling out that -2 from the bottom. And then x to the -2 would be 1 over x squared. So that's if you wanted to write it more neatly. So this is all great. You can also do this. You can also do just general polynomials. It doesn't have to be a monomial. It doesn't have to be a single term. You can do things like the integral of x squared plus 2x plus 1. And this would give you, let's see, you could just do it as 3 separate integrals. You could do it as the integral of x squared dx plus the integral of 2x dx plus integral of 1 dx, which is often just written as the integral of dx without the 1. And you would just do, let's see, x squared becomes x cubed over 3 plus 2x. Well, the 2 isn't really going to do anything. The x is x to the 1. It becomes x squared divided by 2, but we also have that 2 out in the front, so 2x squared over 2. The 2's will just cancel out there. Plus the integral of 1. You can think of the 1 as 1 times x to the 0. You can think of it as 1 times x to the 0. And then x to the 0 goes to x to the 0 plus 1 is 1 divided by 1. You can think of it like that. And of course we still have the 1 out front. So the integral of a constant is just that constant times the variable. Whatever the variable may be, you will know what the variable is depending on what your differential says it is. This tells you what variable you're working with. So this is just going to be plus x, and then of course there's going to be a big plus c at the end. You might be saying, well, wait, if I wrote it as 3 separate integrals, shouldn't I do plus c1 here and a plus c2 here and a plus c3? Sure, you could do that. So you would get plus c1 plus c2 plus c3. But what's the sum of 3 constants? Another constant. So instead of just writing 3 separate constants and adding them, you could just replace them by 1 constant that accounts for all 3. So you're left with, I guess I'll write this as 1/3 x cubed plus x squared plus x plus the big C. Okay, so we can do a lot with the power rule. But there are going to be some things that we can't do so easily. For example, you might think at first glance that you could do something like this. Integral of x plus 1 squared. You might think, well, okay, I'm just going to increase the exponent by 1 and divide by the new exponent. You might think that you can just do x plus 1 cubed over 3 plus c. And you would be wrong. And to see why that would be wrong, well, we already did the integral of x plus 1 squared. X plus 1 squared is x squared plus 2x plus 1. And we know what we get when we integrate x squared plus 2x plus 1. We get 1/3 x cubed plus x squared plus x. Let's see if that's what we get when we try and FOIL this. X plus 1 cubed over 3. So I'm going to have 1/3 and then x plus 1 cubed. Well, I can do x plus 1 times x plus 1 squared, and I already know what x plus 1 squared is. That's just x squared plus 2x plus 1, so saving myself a couple steps there. And if I go ahead and distribute the x, I will get, let's see, 1/3 and then x times x squared is x cubed plus, that's going to be 2x squared, and then x times 1 is just going to be plus x. And then all that plus 1 times x squared plus 2x plus 1. So plus x squared plus 2x plus 1. That's going to be in its own set of parentheses. And then all that, I'm just going to put it in square brackets to show that the 1/3 applies to all of it. Okay, let's see, x cubed, we can leave it alone, plus 2x squared and plus another x squared, that's 3x squared. So that's 3x squared. I guess I'll write it over here because I ran out of space. So 1/3, and then we keep the x cubed, 2x squared plus x squared is 3x squared. And then plus x and plus 2x is plus 3x. And we would just have the plus 1 over there. And if I distribute the 1/3, I would get 1/3 x cubed plus x squared, which looks about right, plus x plus 1/3. And then I guess I left out the plus c from earlier, plus c. Okay, so compare this to this, and you see that we are off by 1/3. Which isn't a lot, but they're not identical. The point is that they're not identical. So what do we do for a situation like this? I mean, in the case of x plus 1 squared, well, that's easy. You just FOIL it like this and integrate term by term. But what if I gave you something like this? What if I gave you the integral of x plus 1, or x plus any number really, to the 10th power? What do we do for cases like that? What do we do for cases like that? Well, this is where another rule of integration comes into play. This is where we take advantage of something called U-Substitution, integration by U-Substitution, which is going to be the focus for today. Integration by U-Substitution. If you know your derivatives, then you have used the chain rule to do derivatives before. You have done the derivative of something like this, and you learned that to do the derivative, you would have to, let me see. I guess I can do it over here. If I wanted to do the derivative of something like this, if I had something like, I don't know, x squared plus 5 to the 7th power, and I wanted to do the derivative of that thing, then you know that you would do the derivative of the outer function being something to the 7th power. X to the 7th would be your outer function, where x was substituted by x squared plus 5. And then you would have to multiply that by the derivative of the inner function here being x squared plus 5. So you would do 7 x squared plus 5 times the derivative of x squared plus 5. Derivative of x squared is 2x, plus the derivative of 5 is 0, so just times 2x. And I guess you could simplify this and make it 14x times x squared plus 5 to the, oh, I forgot, to the 6th power. That was something I forgot. Okay, so U-substitution teaches us how to reverse this process. U-substitution is an integration technique that basically allows us to do the chain rule backwards. So let's see how it works. Let me grab a new sheet of paper and let's see how it works. Let's try and reverse engineer this. Let's try and reverse this process using U-substitution, and we'll also learn why it's called U-substitution at the same time. So we have 14x x squared plus 5 to the 6th. 14x x squared plus 5 to the 6th. If I take the integral of this with respect to x, then what I'm supposed to get is x squared plus 5 to the 7th power. I guess I didn't really talk about that, and I'm not really ready to talk about it. I need some more time to think about how I want to present the idea, but integrals and derivatives are related to each other. They are essentially inverse processes, but not exactly, because actually, I think I did mention this before. I feel like I did talk about this before. Because of this plus c, you've got more than one expression that differentiates to the same value. So differentiation is a one-way process, but integration is a, I guess, multiple-way process, for lack of a better term, because of that plus c. So it doesn't exactly fit the definition of an inverse, but they do, in a more general sense, reverse each other. They undo what the other one does for the most part. So I should be able to get back the original function I differentiated, only differing by a constant. That's what I'm trying to say. So how does the U-substitution method work? Well, basically, when you look at something like this and you think, oh, this is the result of a chain rule, that means that you took the derivative of the inside to get some part of this integrand, which would be this part right here. This part, maybe not all of it, but some of it contains the derivative of this part. So what you want to do, and this takes a lot of practice and skill. Here it's pretty obvious, but we will see soon that it's not always easy to decide what your substitution should be. we need to decide what we want to differentiate so that its derivative will end up being somewhere else within that same integrand. So in this case, I want to substitute x squared plus 5, and we will substitute it with a new variable that we call u. And this is where the name U-Substitution comes from. You don't have to use the letter u. You can use any other variable you want, but u is what we use for tradition's sake, I guess. So I'm going to do u equals x squared plus 5. I'm going to do u equals x squared plus 5. So now I want to take the derivative of this expression. So I'm going to get du dx equals the derivative of x squared plus 5 is 2x plus nothing. Now, math professors will get mad at you if you say this, but essentially you can quote-unquote multiply both sides by dx, and this becomes du equals 2x dx. That's not what's really going on here, but for our purposes, we'll just have to pretend that this is the case. Well, let me think. Can I explain it really quickly? Can I explain why this is the case? Actually, yeah, I can. So here's how I can justify this. Here's how I can justify that this is the case. So essentially what I've done is I've done du equals, well, what is this 2x? It was du dx times dx. I can prove this is true by simply integrating both sides. So if I integrate both sides, then the integral of du is going to be u, right? This is just the integral of 1 du, kind of what we were talking about back here. The integral of a constant is just that constant times the variable. And then integral of du dx. Well, du dx is just the derivative of u as a function of x. This u over here, you can think of it as u of x equals x squared plus 5. And du dx, you can think of it as u prime of x. If you've done derivatives before, you should understand this notation. Okay. So then this would just be the integral of u prime of x dx, but the integral of a derivative is just the function that you differentiated. The integral of u prime of x with respect to x is just u. So u equals u, and we're done. Technically, there are going to be differences because of the plus c, but I'm not entirely sure how I can justify this when you take that plus c into account. I would need to think more about that. The plus c might throw a wrench in things, but I think what I have here should be sufficient to show you that this step, jumping from du dx equals 2x to du equals 2x dx, I think I have sufficiently demonstrated that this is okay. I think I've given you enough to be comfortable with this idea. Okay, let me switch colors actually. So where were we? We defined u as being x squared plus 5, and then we did du dx equals 2x. We differentiated both sides, and then we moved the dx over to the right-hand side. I'm not always going to write this step. In fact, most of the time I'm going to go directly to here. I'm going to go directly from u equals x squared plus 5 to du equals 2x dx. But just for this first example, I figured I might as well show this as an intermediate step. Okay, so du equals 2x dx. What do I do with this? Well, this allows me to find a 2x dx in my integral and replace it with du. So what I'm going to have is, well, let's see, where's my 2x dx? I have it. My 14x can be rewritten as 7 times 2x. And then x squared plus 5 to the 6, well, x squared plus 5 is u, so I can go ahead and rewrite this as u to the 6. And then I've got my dx. Well, I can do 2x dx. I can take out my 2x dx over here. This is all multiplication, right? I mean, the origin of this was Riemann sums. If this was a Riemann sum, it would be something like the sum of 14xi xi squared plus 5 to the 6th power delta x, right? This would have been all multiplication before you took an infinite sum and turned it into this integral. So this is all multiplication. We can move these around. So yeah, taking advantage of the commutative property of multiplication, I can just rewrite this as 7u to the 6 times 2x dx, and my 2x dx can be replaced with a du. 7u to the 6 du. And now I have a new integral in terms of a new variable. My variable and my differential agree with each other. I can solve this. I couldn't do it back here or back here because I had two different variables and a differential that only agrees with one of the variables. But now that I've rewritten everything in terms of the same variable, now that my differential matches the variable in my integrand, we are good to go. Another way you could have gotten here, by the way, is you could take this du equals 2x dx, and you could just divide by 2x and do du over 2x equals dx, and then you could plug this in for dx. So you could do an alternative route. Actually, no, not from here. From the very beginning, from here, you could do integral of 14x, and then x squared plus 5 to the 6 becomes u to the 6, and then replace the dx with du over 2x, du over 2x, and then 14 over 2 reduces to 7, and then x over x cancels out. And you'd end up with 7u to the 6 du. Same result, different routes. So usually I see this approach being used by AP calculus teachers, while the first approach that I showed is more often used by college math professors. So you probably want to get comfortable with this first method anyway, but as a last resort, if you're looking at a complicated looking integrand and it just doesn't look very simple, and you're not sure where to pick out your whatever this turns out to be, whatever your du is, you can't see it, you can't find it in your integrand, then you can go with this. It's not wrong. It's not wrong, but you'll find that once you've learned how to use this more traditional method, actually, I don't want to call it traditional. Once you practice this first method enough, you'll start to find that it's actually a little bit faster than doing this. At least in my experience, it's faster. But, you know, accuracy before speed. If it comes at the cost of your accuracy, it's not worth it to be fast. So do whatever works for you. But I would advise eventually learning to do it this first way. Okay, so 7u to the 6 du. I can integrate this pretty easily using the power rule. U to the 6 becomes u to the 7. So it becomes, let's see, 7, and then u to the 7 over 7, plus c. And the 7's cancel out. And u to the 7 plus c, u to the 7 plus c, can be rewritten back in terms of x. My u was x squared plus 5, so now I can rewrite this back as x squared plus 5 to the 7 plus c, which should be, yep, exactly what I differentiated to get this integrand to begin with. All right. So that's basic U-substitution. The idea is that if you look at your integrand and you notice that parts of it look like they came from the derivative of other parts of it, then you assign that other part to u and you take its derivative so that you can then find that derivative, or at least some multiple of that derivative, in the rest of your integrand and move that out with your dx to turn it into a du, and then everything's all hunky-dory. But that's not the only case you'll have that calls for U-substitution. Sometimes it won't be very obvious what you should use for your u. Sometimes it's not going to be very obvious. And that's what this is for. So this is something I found online a couple years ago. It's from a professor at UC Davis. I will post the link to this page. I actually have it downloaded as a PDF because I was worried that the page would, get taken down at some point. But he goes over he goes over basic U-substitution, of course, and eventually he goes over, where is it? Right here. So starting from problem 13, he says, well, I assume it's a he, but this professor says, the following problems require U-substitution with a variation. I call this variation a back substitution. It's in air quotes because I think it's not an official term. For example, if u equals x plus 1, then x equals u minus 1 is what I refer to as a back substitution. So that's what this professor says. And we're going to work through these integrals. And of course, you can click to see the solutions if you go on the web page. But yeah, that's what we're going to be doing. I'm going to pick a few of these, or maybe I'll do all of them. Who knows? We'll see. But first, let's do a couple of normal substitution problems. So I'm going to go ahead and switch back to my camera. And I'm going to pick out a few of these and see what we can do with them before we look at those really weird, well, I mean, they're not that weird once you get used to them, but those back substitution problems. So let me pick a color here. How about light blue? Ow. Poked myself with my own pen. Great. And how about that first one? So it says 2x plus 5 times x squared plus 5x to the 7th. So, well, I didn't word that very nicely, but you'll understand once you see it written. So it says 2x plus 5 in parentheses integral of 2x plus 5 multiplied by the quantity of x squared plus 5x to the 7th power and integrated with respect to x. How would we do this one? Well, we look at it and we see that's to the 7th power. We would be here all day if we tried to just FOIL this out. You can, and it'll work, but it's time consuming. But fortunately for us, if you look over here, 2x plus 5 appears to be the derivative of x squared plus 5x. So maybe I should use u equals x squared plus 5x, which would give me du equals derivative of x squared is 2x plus derivative of 5x is 5. So that's 2x plus 5 dx. I think these parentheses are important. A lot of people neglect to write them, but it really should be this whole thing times dx. Anyway, I have a 2x plus 5 dx. It's this. So this is 2x plus 5 dx. That's going to turn into a du. And x squared plus 5x, that's going to turn into a u. So that's going to be a u to the 7th. And then 2x plus 5 dx is gone and replaced by du. Now I can integrate this easily using the power rule. U to the 7th becomes u to the 8th over 8 plus c. So that's 1/8 of, let's see, u to the 8. U, I need to change back, now that the integration is done, change back to x squared plus 5, and then to the 8th, and plus c, and we're done. Okay, here's one that is, well, it's less obvious what you have to do for U-substitution, but, well, I think it's easier to just show rather than tell. So for this one, what color do I want? Let's do this purple color. So this next one is integral of 3 minus x quantity to the 10. 3 minus x to the 10 dx. Okay, you look at this and you go, wait a minute, I don't see a derivative in here anywhere. Well, that's because the thing that you can take the derivative of will give you a derivative that's a constant. And with constants, you don't really need it to already exist within your integrand, because you can just, if you need a constant to go into your, if you need this thing that gets taken away with your dx, if you need it to be a constant, you can always just put that constant in there, as long as you also cancel it out somewhere else. So if I look at 3 minus x to the 10, I would love for this to be u to the 10. So this is going to be my u. At least I would hope that my u is going to be 3 minus x. But if I take its derivative, I get du equals derivative of 3 is 0, derivative of x is -1 dx. I don't have a -1 in here. Well, that's okay, because I can multiply this by -1 over -1. This is allowed. You are allowed to multiply by a constant as long as you also divide by it. And now I can take -1 with dx and turn that into a du. So I'm left with integral of u to the 10th over that leftover negative 1 that didn't get taken, and then this negative 1 did get taken with the dx to form a du. Dividing by negative 1 is the same as multiplying by negative 1. It just leaves you with a negative, so this is just integral of negative u to the 10 du, and from there it's all smooth sailing. You get negative u to the 11 over 11 plus c, and substitute back for x now that the integration part is done, and you get negative 3 minus x to the 11 all over 11 plus c. Is that part of the page even visible on the screen? Now it is. I try to avoid writing that low, but sometimes you have to. And let me draw a little squiggle here to separate those from each other. And there we go, that takes care of that one. Next one, we've got a square root. So I will do this on the next side. It says square root of 7x plus 9 dx. Well, I know how to take square root of x dx. I know how to integrate square root of x dx, but square root of 7x plus 9? Square roots become really, really annoying with integration once you start having addition and subtraction within the square roots. When you see some sort of expression under the square root, it's time to consider other integration methods, because square roots, they're quite notorious. You'll learn, if you haven't been doing a lot of calculus already, you'll quickly learn in your calculus class that square roots are not something you want to mess around with. Sometimes they're just straight up, well, actually, let me think. I guess it depends on what's in the square root, but some of them might actually just be impossible to integrate. Like, the best you can do with them is approximate them, and they are not the only category of functions that don't have a closed form integral. There are a lot of functions for which there is no integral, and the best you can do is just use approximation. Engineers are happy about this because approximation, you can just approximate to whatever level of precision you need. Even though it'll never be perfect, engineering doesn't really live in the world of perfect. Engineers live in the world of good enough. So engineers are happy about it, but scientists maybe not so much. Anyway, I'm going to, I guess in this case, I just want to simplify what's inside the square root and simplify it down to one term. I don't like having that plus 9 in there, but I do know the derivative of plus 9 is 0, so if I do u equals 7x plus 9, then I get du equals derivative of 7x is 7, and then derivative of 9 is 0, and then dx. Du equals 7 dx. Okay, and I can just multiply and divide by 7 here, so I can multiply by 7 over 7. I know I didn't write it inside the integral, but I can move constants in and out of the integral as I please. I can move them in and out as I please, as long as they are constants. So we can do this 7 dx becomes du, and then I have the 1 over 7, and then square root of 7x plus 9 becomes a u, 7 dx becomes a du, And we did the integral of a square root earlier. It's 1/7 integral of u to the 1/2 du, which becomes 1/7 integral of, or not, no, I don't need to write the integral symbol again, which becomes 1/7 u to the 1/2 plus 1 is 3/2 divided by 3/2, and then plus c. Now, does the 1/7 distribute over the plus c? You can do that. You can do 1/7 of this stuff plus 1/7 of c, but 1/7 of c is just a different c. So why bother? This is an arbitrary constant, and 1/7 of an arbitrary constant is another arbitrary constant. So there's no actual point to multiplying it by 1/7. If you had enough information to figure out what c is, multiplying it by 1/7 would just make it 7 times bigger to compensate. So yeah, there isn't really much of a point to doing that. Anyway, I want to simplify this. So dividing by 3/2 is the same as multiplying by 2/3. 2/3 times 1/7 is 2/21. You don't have to do this, but it's good to get in the habit of doing this. And then u to the 3/2 plus c. And come to think of it, I don't think I did that with the first example I did. Yeah, so all the more reason to do it here. And then u to the 3/2 is u cubed under a square root. So this is just going to be 2/21 square root of u cubed plus c. And yes, you can move the cube outside of the square root. Like I said towards the beginning, reviewing your rules of exponents might be worthwhile. It definitely comes in handy here. This is why people say that calculus is mostly algebra, because it's actually true. The calculus part is not the hard part. The hard part is the algebra. Most of the time anyway. Okay, so I guess, we're not done. We have one more step. Rewrite in terms of x. So u was 7x plus 9, so this becomes 7x plus 9. Quantity cubed, all under the square root, and plus c. All right. I think that is enough of the simple substitution problems. Now let's go and look at those back substitution problems. Let's see how those work, and I'm going to pick the ones that don't use the types of functions that I haven't really discussed yet, logs and whatnot. Maybe we'll discuss that later, but let me think. Well, for physics C, I doubt they will give you, well, okay. Yeah, we will have to discuss them. Okay, I'm remembering. We're going to have to do integrals and derivatives involving like logs and trig functions and exponentials sometimes. So yeah, I'm going to have to plan out a lesson for that probably. Either that or I'm going to wait until I get to the calculus part of physics C. Anyway, first thing they give us is x plus 3 times the quantity of x minus 1 to the 5th power. So this is under that back substitution category, so let's practice with this back this back substitution technique. X plus 3 times, and then we've got x minus 1 to the 5th. And we're integrating this with respect to x. Well, I don't see one of these being the derivative of the other. I don't see anything in here that is the derivative of something else in here. And furthermore, my two most immediate options for you, the two options that pop out to my mind at least, x plus 3 or x minus 1, they both have derivatives that are constant. A derivative of 1. So how do I eliminate the other x? This is where back substitution comes into play. So I'm going to want my x minus 1 to become u, because I really don't want to FOIL x minus 1 to the 5th power. Definitely don't want to spend time multiplying that out. So I'm going to do u equals x minus 1. And that gives me du equals, well, 1, and then that's going to have a derivative of 0, so you're just left with 1 dx. I would just write du equals dx most of the time, but for today I will deliberately write the 1 just so that I can help you ease into it. Okay, so, well, 1 dx, I already have it. It becomes du. And then x minus 1 to the 5th is u to the 5th. Okay, great. And what about x plus 3? I don't have to eliminate x plus 3. I just need everything to be in terms of u. I just need x plus 3 to agree with my differential. After all, this is single variable calculus. Multivariable calculus is going to be a separate course. I just need my x plus 3 to agree with my u. So can I rewrite x plus 3 in terms of u? Yes, I can, because u equals x minus 1 can be rewritten as u plus 1 equals x. And if I make this substitution, then I get integral of u plus 1 plus 3, u plus 1 plus 3, u plus 1 plus 3 times u to the 5th du. Okay, well, this is starting to look awfully messy. Weren't we trying to avoid a mess? Well, let's continue writing this out, and we'll see that it's actually not as messy as the alternative. So you would have u plus 4 times u to the 5th. So this becomes integral of u plus 4 times u to the 5th du. And u to the 5th can be distributed, and it's actually a very simple polynomial from there. U to the 5th times u is u to the 6th, plus 4 times u to the 5th is just 4 times u to the 5th du. If you want to put these in parentheses, you can. And now we just integrate term by term, so I'll do that here. Let's switch colors. Green. So u to the 6th becomes u to the 7th over 7, plus 4u to the 5th becomes u to the 6 over 6, and of course plus c. So that becomes 1/7 of x minus 1 to the 7 plus 4/6 is 2/3, and then x minus 1 to the 6th and plus c. Did I do all that right? X minus, yeah, u equals x minus 1. And that's to the 7th over 7. That's to the 6th over 6. 4 over 6, 2/3. Okay, yeah, it all looks good to me. All right, let's move on to the next one. So the next one says take the integral of x times the square root of 4 minus x. Integral of x times the square root of 4 minus x. Okay, so I want to simplify what's inside the square root. That would be my best option. So let's see if we can do that. We can do u equals 4 minus x, and that gives me du equals negative 1 dx, which would give me x times square root of u. I'm going to go ahead and rewrite it as u to the 1/2. And then for my dx, if I want a negative 1 dx, then I can just multiply by negative 1 over negative 1. And then I can take this negative 1 dx and replace it with a du. So I get 1 over negative 1 is left. And then integral x u to the 1/2 du. Took away the negative 1 in the dx. And now I need to get rid of this x somehow. And I can do that again using this back substitution technique. If we add, well, let me see. Yeah, add x and subtract u. So I would get x equals 4 minus u. And if I plug that in here, then I'm left with 1 over negative 1 is negative 1, so, whoops, too high. There we go. I blocked my own view with my hand and didn't realize I had all this up here. Equals 1 over negative 1 is negative 1, so I'll just have a negative sign, and then integral, and then x is 4 minus u times u to the 1/2 du. I can distribute u to the 1/2. Not exactly a polynomial expression because of the rational exponents, but something that can be broken down into a sum or difference of multiple integrals. Okay, negative u times u to the 1/2. So u to the 1 times u to the 1/2 is u to the 1 plus 1/2, or u to the 3/2. And then du. And now we just power rule our way through this. So we're going to have negative 4 u to the 1/2 becomes u to the 3/2 over 3/2 minus u to the 3/2 becomes u to the, let's see, 3/2 plus 1 is 3/2 plus 2/2 is 5/2 over 5/2, and then plus a c. And again, the negative sign, I could distribute it to the plus c, but the negative of a constant is just another arbitrary constant. Since we don't know what c is anyway, it doesn't matter whether we multiply it by a negative. the negative of c is just going to be a different c. Okay, I think I have enough room left over to finish it off right up here. So 4 over 3 halves is 4 times 2 thirds is 8 thirds. So 8 thirds, and then u to the 3 halves. That's 4 minus x to the 3 halves. I think I'm just going to keep it as that, 4 minus x to the 3 halves. And then that's, wait, and I forgot the negative, yeah, distribute the negative to it, so negative 8 thirds, and then distributing the negative to this makes it a plus, and then u to the 5 halves over 5 halves, that's the same as multiplying by 2 fifths, and then 4 minus x to the 5 halves, and of course plus c. And we're done there. Okay, let me look at this next one. Does this next one require logarithms? I think it does. I think it does. Maybe I will skip on it then. Actually, I think all of these will. All of the remaining ones. You know what? I'll go over it. I'll go over logs real quick. So, the power rule works for negative exponents, we said, right? Well, there is one specific negative exponent that it does not work with, and that is negative 1. The integral of x to the negative 1 does not follow the power rule. It does not obey the power rule. If you try the power rule on it, here's what you're going to get. X to the negative 1 plus 1 over negative 1 plus 1. Do you see the issue? Division by 0. That doesn't look right. But we do know a function, if you already learned derivatives, we do know a function whose derivative is x to the negative 1. Or rather, a function whose derivative is, another way of writing x to the negative 1, is 1 over x. What function has a derivative of 1 over x? Well, that would be the natural log function. That would be the natural log function. So this is just going to be natural log of x, usually written as natural log of absolute value of x, because you can't take the natural log of a negative, plus c. So if you have 1 over something, it integrates to a natural log. And we will deal with sines and cosines at a later time, I guess. But, well, I mean, I can talk about that here. So the power rule also doesn't work for functions that are not power functions. For example, the integral of something like sine of x or cosine of x, these don't follow the power rule. These don't follow the power rule at all. These just have their own separate integration rules because they also have their separate differentiation rules. You didn't differentiate them using the derivative version of the power rule either. You would just have to resort to memorization here. You might remember that the derivative of sine of x equals cosine of x, while the derivative of cosine of x equals negative sine of x equals negative sine of x. So then you would do the antiderivative of sine of x would be, well, negative sine of x comes from positive cosine of x. So positive sine of x would have to come from negative cosine of x. Plus a constant. And then over here, integral of cosine of x. Cosine of x comes from differentiating sine of x. So this equals sine of x plus a constant. Okay, what else? I guess exponential functions, since we're talking about all the different functions. Exponential functions. So you would have the integral of e to the x. This one's actually pretty simple. The integral of e to the x is e to the x plus a constant, because the derivative of e to the x is e to the x, which is something I would assume you already learned well before watching this video. At least I would hope. But if you're just coming from, AP Physics and you haven't learned any calculus yet, then you'll just have to take my word for it that this is the case. And what about exponential functions with different bases? I don't think you're really going to encounter that in physics. So I would really like to leave that alone for now. Yeah, I'm going to leave it alone. I think this will be more than enough for physics purposes. Okay, so now that we've covered all that, let's go back to our next back substitution problem. So it says, integrate x plus 5 over 2x plus 3. Take the integral of x plus 5 over 2x plus 3. And I'm pretty sure this is going to involve some sort of logarithm. Actually, maybe not. So I think what I want to do for my u, I think I want my u to be 2x plus 3. Let's see how that works out for me. Oh, or maybe... Okay, I'll work with this for now and see how it fares before trying the other option. So u equals 2x plus 3 gives me du equals 2 dx. I can multiply by 2 over 2 and take the 2 with the dx and replace that with du. So I get 1/2 integral 2x plus 3 just becomes u, and then 2 dx, that's du. Oh, it might not actually be a natural log at all. X plus 5. To solve this for x, I would subtract 3 and divide by 2. So u minus 3 divided by 2 is 1/2 u. Actually, I'll do this. 1/2 on the outside and then u minus 3 equals x. Yeah, and I'll just keep it like that. So I'd have 1/2 u minus 3 plus 5. Okay, and I would have to... I'd have to... Well, instead of distributing the 1/2, I can multiply by 2 over 2 again. So I'm going to multiply by 2 here. I'm going to multiply all this by 2 and also divide by 2 on the outside. So that gives me 1/4 integral of u minus 3 plus 10 over u du. U minus 3 plus 10, that's u plus 7. U plus 7 over u. So that's going to be 1/4 integral of u plus 7 over u. U over u is 1, plus 7 over u is, well, 7 times 1 over u is how I'm going to write it. Du. Okay, yeah, it's going to involve a logarithm. So the integral of 1 is just the variable, which is u. So 1/4 times, that's going to be u, plus 7 times the integral of 1 over u. The integral of 1 over x is ln of x. The integral of 1 over u is ln of u. So that's 7 natural log of u. And plus c, and I can distribute the 1/4, and I want to rewrite the u. So 1/4. Oh, wait, what did I do? Distribute the 1/4. 1/4 of 2x plus 3 plus 7/4 natural log of the absolute value of 2x plus 3. In case x is equal to, what, negative 1.5 or less, I would need these absolute value bars to be here. Well, not negative 1.5 or less, just less than negative 1.5, because at negative 1.5 you can't take the natural log either. Can't take the natural log of 0. And then of course plus c. And as I said time and time again, distributing the 1/4 to it would be pointless because you just get a c of a different kind. All right. Next one says x squared plus 4 over x plus 2. Oh my, and the one after that. I'm not entirely sure. Well, actually, I think I know exactly what to do with that one. That one's going to be quite the high note to leave on. So we have x squared plus 4 over x plus 2, integral of x squared plus 4 over x plus 2 dx. What do I want to use here? Actually, I think I'm going to use x plus 2, because if I turn this into a u, and I can replace this x with whatever it is, x minus 2, 2 minus x, whatever it turns out to be. And then I'm going to get something kind of similar to what happened here, where you're going to get some polynomial in the top divided by a u in the bottom, which is just going to be well, maybe not a polynomial, but it's going to be a sum of terms that I can integrate easily. So yeah, I think x plus 2 is going to be my U-substitution here, which gives me du equals 1 plus nothing, so just 1 dx. Du is simply equal to dx, so that becomes integral of, and I'm going to go ahead and set up my back substitution, so x is going to equal u minus 2. U minus 2 equals x. If I simply subtract 2 on both sides there. So x squared, that becomes u minus 2 squared. plus 4 over x plus 2 is just u, and dx, or 1 dx just becomes a du. And yeah, we're in business. U minus 2 quantity squared, that's easy enough to FOIL, equals integral of u squared minus 4u plus 4, and then plus the other 4 on the outside, all over u du. Okay, so that's u squared minus 4u plus 8 over u. U squared over u is just u. Minus 4u over u is minus 4. And then plus 8 over u is, well, plus 8 over u du. Okay, integral of u to the 1 is u to the 2 over 2, so that's going to be u squared over 2, and then minus integral of 4 is just 4u, and then plus 8 integral of 1 over u is natural log of u. Natural log of absolute value of u. And of course, we would have our plus c hanging out there. And yeah, I would be in the habit of writing the 2 in this denominator as a 1/2, but I'm not going to waste an extra line to write that one out. We're good there. Okay, this next one looks like a nightmare. Do I have... Yeah, I have the back side of this sheet to work with. Let's go for... I don't think I've used the orange in a while. So this one says, take the integral of 3 plus the natural log of x squared. My goodness. Take the integral of 3 plus the natural log of x all squared times 2 minus the natural log of x all over 4x dx. Okay, well, clearly my U-substitution is going to be one of these two. And the x in the denominator is not a coincidence, because if my U-substitution is going to be one of these expressions involving the natural log of x, its derivative is going to have something over x dx, and this x in the denominator is going to get pulled out with the dx to make my du. If you can't see that right away, don't worry, it'll become apparent in a second. So which one is the better choice for you? I think it would be this first one, because then it will simplify to a u squared and I won't have to FOIL anything. So I'm going to try the first one. U equals 3 plus natural log of x. If I take the derivative, then I get du equals, derivative of 3 is nothing, derivative of natural log of x is 1 over x. And then, of course, dx. Okay, now if I back substitute, I want to solve for, I don't want to solve for x, I want to solve for natural log of x. So natural log of x is going to be u minus 3. If I subtract 3 on both sides here, u minus 3 equals natural log of x. Okay, if I put that into here, what do I get? Well, first of all, let me find my 1 over x dx. I have it. It's right here. This is my 1 over x, and there's my dx. We're done. We found our du. So integral of, that's going to be a u squared, and then 2 minus natural log of x. That's 2 minus u minus 3. And we still have that 4 in the denominator. And yeah, the x in the bottom and the dx got taken out and replaced by a du. Okay. And then 2 minus u minus 3, well, 2 minus negative 3 is 5, so that's going to be 5 minus u. And the 4, I guess I could factor it out of the entire integral. So yeah, I'll do that. 1/4 of u squared times 5 minus u du becomes 1/4 of the integral of 5u squared minus u cubed du. And then just power rule for the rest. So that's going to be 1/4 of 5u cubed over 3 minus u cubed becomes u to the 4th over 4, and plus c. So that's, wait, 5 over, let's see, 1/4 times 5 over 3, that's 5 over 12. Yeah, that doesn't reduce by anything. 5 over 12 u cubed minus, actually, wait a minute, did I? Oh, I just realized I forgot to resubstitute for my u over here. It just dawned on me. So this is going to become what? X plus 2 squared over 2? Man, how did I miss this? So that's going to be x plus 2 squared over 2 minus 4 x plus 2 plus 8 natural log absolute value of x plus 2, and then plus c. Okay, there we go. So for those who were yelling at me for that one, relax, I fixed it. And then, where were we? 1/4, and then distribute to the negative u to the 4th over 4. That's going to be negative u to the 4th over 16. 1/16 u to the 4th plus c. And finally, five twelfths. U cubed is 3 plus natural log of x cubed minus 1/16 3 plus natural log of x to the 4th plus a constant. Okay, and there we go. Hopefully this has been helpful. I'm going to think a little bit about what I want to do for next time, but it will probably be going back to more examples of Riemann sums unless I can think of anything else that ought to come first. So yeah, I'll have a week to reflect on that, but considering how busy my days have been lately, I might not even find the time to reflect on it well enough. So chances are it's going to be haphazard and I'm just going to roll in without a plan. But we'll figure it out when we get there next week. Hopefully this has been helpful. Take care, and I will see you in the next one.